Hello, friend. Welcome to Science for Sleep. Did you know that most of the universe is made of things that do not emit light at all? When you look up at the night sky, nearly everything you see is glowing. Stars shine because they produce energy. Galaxies appear because billions of stars are clustered together, sending light outward across space. Even distant clouds of gas glow faintly when nearby stars illuminate them. What reaches your eyes is the visible part of the universe, the part that announces itself through light. But now, imagine all the things that do not glow. Planets like Earth do not produce their own light. Moons do not shine on their own. They only become visible when light falls on them. Asteroids, dust, cold gas, and entire regions of space remain dark unless something nearby happens to illuminate them. And beyond these familiar objects, there are vast amounts of matter that never emit light at all, no matter where they are. Most of the universe exists in this quiet state, present, massive, and real, yet invisible to the eye. This means that what we see when we look into space is only a small portion of what is actually there. The bright points and glowing swirls are not the full picture. They are highlights, brief signals rising out of a much larger, darker whole. The universe is not defined by what shines, but by what endures quietly in the background. If you enjoy these quiet journeys, you're welcome to subscribe, and if it feels natural, to leave a comment sharing where you're listening from tonight. It helps others find their way to this calm corner of the world, one sleepy traveler at a time. The quiet continues here, just as it is. Tonight, we're going to spend some quiet time with the universe. Sometimes it feels distant. Sometimes it feels dramatic. Beneath those impressions, it moves in slow, steady ways that never rush and never react. Changes unfold across enormous spans of time, following consistent physical rules that do not depend on observation or response. The universe includes all space, all time, all matter, and all energy that exists. Nothing sits outside of it. Nothing contains it. It is the full setting in which every star, planet, and particle takes its place. Scientists estimate that this universe is about 13.8 billion years old, giving it more than enough time to expand, cool, and settle into the patterns we observe today. Light helps us understand these patterns, but it also places limits on what we can know directly. Light moves at a constant speed, and because it takes time to travel, it carries information from the moment it was created. When light reaches Earth, it brings a record of where it came from and when it began its journey. Light from the sun arrives in about 8 minutes. Light from distant stars may take years or longer to reach us. Some of the light visible in the sky tonight began traveling long before Earth formed. Other parts of the universe remain unseen, not because they are absent, but because their light has not reached us, or because they do not emit light at all. The region we can observe is called the observable universe. It is defined not by an edge, but by distance and time working together. Beyond it, space may continue in ways we cannot yet measure. This is not something to resolve or picture fully. It is simply how observation works in a universe where light and time are linked. As we continue, we'll explore the universe gently, one idea at a time. There's nothing you need to hold on to. These thoughts can pass through the mind slowly, the way light passes through space, steady and unhurried. The universe does not change its course based on how closely it is observed. It simply continues, carrying its unseen majority alongside the parts that glow. Light is how the universe shares information. It does not hurry, and it does not pause. Once light is created, it moves forward at a fixed speed, crossing space steadily, regardless of where it is going or how long the journey will take. There is no faster path and no slower one. Every particle of light follows the same rule, traveling through the open structure of space without sound, resistance, or deviation. Because of this, light becomes a kind of messenger. It carries details about where it came from and what was happening at the moment it was released. When light reaches Earth, it arrives unchanged by distance alone. What has changed is time. The farther light travels, the longer it has been moving, and the older the information it carries becomes. This means that space is layered with moments. Nearby light represents recent events. Distant light represents events that took place long ago. When you look at a nearby star, you are seeing it as it was only a short time in the past. When you look at a distant galaxy, you are seeing it as it was millions or even billions of years ago. The universe does not present itself all at once. It reveals itself in slices arranged by distance. Light from the sun reaches Earth in about 8 minutes. During that time, the light moves silently through space, crossing the gap between the sun and the planet without slowing. If the sun were to change in any way, that change would not be visible immediately. There would always be a short delay, carried by the time it takes light to arrive. Light from the nearest star beyond the sun takes more than 4 years to reach us. That means the light entering your eyes tonight began its journey when the world was slightly different than it is now. On larger scales, this effect becomes more pronounced. Light from distant galaxies may have been traveling since long before Earth formed. Some of it began its journey when the universe itself was young. Because of this, the universe cannot be seen as it exists in a single moment. What we observe is a blend of many different moments layered together by distance. Space becomes a record, and light is the ink that writes it. Light does not age as it travels. It does not grow tired or fade because of time alone. It continues forward until something absorbs it, reflects it, or redirects it. In the emptiest regions of space, light can travel for billions of years without interruption, moving through darkness that offers no resistance. Space itself does not carry light the way air carries sound. There is no medium pushing it along. Light moves because that is its nature. Even in near total emptiness, it continues, steady and precise, following the structure of the universe as it expands. This constant speed creates a limit on what can be observed. There is only so far light has been able to travel since the universe began. That distance defines the observable universe. Beyond it, space may continue, but its light has not yet arrived. Not because it is blocked, but because there has not been enough time. As the universe expands, space itself stretches. Light traveling through this expanding space is gently stretched as well. Its wavelength grows longer over time, shifting toward lower energy. This process happens gradually, without disturbance. Light does not resist it. It simply adapts to the changing shape of space. This stretching is subtle but measurable. It tells scientists how space has expanded and how the universe has changed over long spans of time. Light carries this information quietly, without effort or intention. It is simply what happens as space grows. There are many kinds of light, even though human eyes can detect only a small portion of it. Beyond visible light, there are longer wavelengths and shorter ones, each interacting with matter in different ways. Some forms of light pass through dust easily. Others reveal heat. Others trace magnetic activity or energetic events. Each type adds depth to our understanding, not by changing what exists, but by revealing different aspects of it. Still, most light travels unseen. It moves through space whether or not it is detected. It continues through regions with no observers, no instruments, and no destinations. Light does not require recognition. It does not depend on being noticed. It simply follows the rules that govern it. As these waves of light move outward, the universe continues to expand around them. Space stretches. Distances increase. Yet light remains consistent, marking time through motion alone. It is one of the few things in the universe that behaves the same way everywhere, providing a steady reference across vast scales. As you rest here, there is nothing you need to track or measure. You don't need to picture exact distances or imagine specific paths. It's enough to know that light moves steadily, carrying moments across space, connecting distant places without effort or change. The universe reveals itself slowly, one arrival at a time. And as light continues its long journeys through space, we can allow our focus to soften, knowing that these processes unfold, whether we observe them closely or not. Light moves on. Space stretches. Time continues forward. And everything remains held within the same quiet structure. As light continues its steady movement through space, it naturally defines how much of the universe can be known directly. There is a practical boundary created by time and distance working together. Not a wall, not an edge. Simply a limit shaped by how far light has been able to travel since the universe began. This region is called the observable universe, and it exists because the universe has a finite age combined with a constant speed for light. From Earth, this observable region extends outward in every direction. Wherever you look, you are looking as far as light has been able to reach you. The farther away something is, the longer its light has been traveling. Eventually, distance becomes so great that light has not yet had enough time to arrive. The observable universe is vast. Its diameter is estimated to be about 93 billion light-years. This number reflects expansion as well as travel time, since space itself has been stretching while light moves through it. Even as light journeys forward, the distances it crosses gently increase. What lies beyond this observable region is not known directly. Space may continue far beyond what can be seen. It may extend much farther than current observation allows. The absence of visible information does not suggest absence of matter or structure. It only reflects the limits created by light and time. In this way, observation depends on patience rather than reach. The observable universe contains galaxies arranged in patterns that repeat across enormous distances. Clusters of galaxies gather together. Long filaments of matter stretch between them. Wide regions with very few galaxies sit quietly in between. These patterns emerge not because of design, but because gravity has been shaping matter for billions of years. Even within this observable region, much remains unseen. Most matter does not emit light. It reveals itself only through how it influences motion. The universe presents itself partially through brightness and partially through effect. What can be seen directly is only one layer of what exists. Light gives shape to the visible universe, but it also reminds us that visibility is selective. Stars shine, galaxies glow, yet the majority of matter remains dark, participating without announcing itself. The observable universe is not the complete universe. It is simply the portion that has had time to speak through light. As the universe continues to expand, the observable region changes slowly. New light reaches us from areas that were once too distant. At the same time, very distant regions move farther away as space stretches. Over extremely long spans of time, parts of the universe may drift beyond what can ever be observed again, not because they disappear, but because their light no longer arrives. These changes occur gradually. They do not happen suddenly or sharply. Expansion unfolds evenly, and observation adapts quietly alongside it. Within the observable universe, physical laws remain consistent. Gravity behaves the same way everywhere it has been measured. Light follows the same paths. Matter responds to the same forces. These consistencies allow scientists to understand distant regions using the same principles that apply nearby. Still, there is no requirement to resolve what lies beyond observation. The universe does not ask to be fully known. It continues regardless of what is measured, recorded, or understood. The observable universe is a window, not a boundary of existence. As you rest, there is no need to imagine distances precisely or picture the full scope all at once. It's enough to sense the idea of reach, light traveling outward, space stretching gently, a region of visibility surrounded by more space, continuing beyond it. The universe does not rush to reveal itself. It allows information to arrive in its own time, carried steadily by light. Some parts have already spoken. Others remain quiet, waiting without effort or intention. And within this calm unfolding, the observable universe simply exists as the portion that has arrived so far, held within the same steady structure as everything else, known and unknown alike. Beyond what can be observed, the universe continues to change in a steady and uniform way. Space itself is expanding. This expansion does not originate from a single location, and it does not move outward from a central point. Instead, space stretches evenly in every direction at once. Wherever you are in the universe, distant regions appear to move farther away over time, not because they are traveling through space, but because the space between them is slowly increasing. This is a subtle idea, but it becomes easier to sense when imagined gently. Picture points of light suspended in darkness. As time passes, the distance between each point grows, even though the points themselves remain in place relative to their immediate surroundings. Nothing rushes. Nothing pulls away sharply. The entire structure simply relaxes outward. Because expansion happens everywhere, there is no preferred viewpoint. Every galaxy observes other galaxies moving away in much the same way. There is no special location where expansion began, and no edge toward which it moves. Expansion is a property of space itself. unfolding uniformly across vast distances. This means that galaxies are not scattered by an outward force. They are carried along by the gradual stretching of space. On smaller scales, gravity holds systems together. Stars remain bound within galaxies. Planets continue their paths around stars. Expansion becomes noticeable only across immense spans of distance, where gravity no longer dominates. Over time, this stretching increases the space between galaxy groups. Light traveling across expanding space is affected as well. As space stretches, the light moving through it stretches slightly too, lengthening its wavelength. This change happens gradually, without disruption, and it leaves a measurable imprint that reveals how much expansion has occurred. This stretching of light does not weaken its journey. It simply changes its form. The light continues forward, steady and intact, adapting to the changing shape of space around it. Through this process, the universe carries a record of its own growth, written quietly into the light that fills it. Expansion has been happening since the universe was very young. In its earliest state, space expanded rapidly. Over time, the rate of expansion changed, guided by the balance between matter, energy, and the structure of space itself. These shifts unfolded across billions of years, shaping the large-scale patterns we observe today. What is important here is not speed or scale, but consistency. Expansion does not surge or stall. It proceeds smoothly, governed by physical relationships that remain stable over time. The universe grows not through sudden movement, but through continual change that remains evenly distributed. As space expands, distances grow larger, but the universe does not thin into emptiness. Matter remains present. Energy continues to exist. What changes is how spread out everything becomes. The same components occupy a larger volume, creating a universe that slowly becomes more spacious over time. This growing spaciousness affects how galaxies interact. Over long periods, clusters drift farther apart. Connections loosen gently. Motion slows, not because of resistance, but because distances increase. These changes happen on timescales so long that they are nearly imperceptible from moment to moment. There is no signal announcing expansion as it occurs. No sound accompanies it. No visible shift marks its progress. Expansion is inferred through careful observation of light and motion, through patterns that reveal themselves only when viewed across great distances and long periods. For the universe itself, expansion is simply part of how it exists. As you rest with this idea, there is nothing to follow or track. You do not need to imagine movement or growth in detail. It is enough to sense space gently opening, distances easing apart, and the universe continuing in a calm, uniform way. Space stretches, light adapts, matter remains present. Everything continues within the same steady framework, changing slowly without effort or disturbance. Within this expanding space, matter does not distribute itself randomly. Over long spans of time, gravity gently gathers material into large, recognizable forms called galaxies. A galaxy is a vast system made of stars, gas, dust, and unseen matter, all held together by gravity. These systems form naturally wherever matter becomes slightly denser than its surroundings, allowing attraction to do its slow work. Galaxies come in many shapes and sizes. Some are wide and flat, with graceful spiral arms extending outward from a bright center. Others are rounder and more compact, with stars moving in smooth, layered paths. Still others appear stretched or irregular, shaped by long histories of interaction and gradual change. Each form reflects the conditions under which the galaxy developed and evolved. There are hundreds of billions of galaxies within the observable universe. Each one contains its own internal structure and motion. Some galaxies hold millions of stars. Others contain hundreds of billions or even trillions. Within them, stars orbit slowly around a shared center, following paths shaped by gravity rather than direction or intent. Galaxies are not isolated objects. They exist within larger groupings. Some gather into small collections, while others are part of massive clusters containing thousands of galaxies. These groupings form because gravity extends across great distances, quietly linking systems that formed near one another. Between galaxies lies space that appears empty at first glance. Yet even these regions contain thin traces of gas, dust, and unseen matter. Nothing is entirely separate. Everything participates, even when it does not shine or announce itself. Within galaxies, stars are arranged in patterns that reflect both motion and time. Younger stars often appear in flatter regions where gas and dust remain available for new formation. Older stars drift into broader, more rounded distributions, carrying long histories within their steady movement. These arrangements change slowly, shaped by countless orbits completed over billions of years. Galaxies also change through interaction. When galaxies pass near one another, their shapes can shift. Stars may be gently redirected. Gas clouds can compress or spread. Over very long periods, galaxies may combine, forming larger systems that carry forward the material of both. These processes unfold gradually, without sudden transitions. Despite their size, galaxies move calmly. Their motion through space is slow, guided by gravity and the expansion of space around them. From within a galaxy, these movements are nearly impossible to sense directly. Stars continue their paths. Planetary systems remain stable. Local motion dominates over distant change. The light that reaches Earth from galaxies carries information about their structure and history. The brightness, color, and distribution of that light reveal how stars are arranged, how fast they move, and how the galaxy has changed over time. Yet even here, light shows only part of the picture. Much of a galaxy's mass does not emit light and can only be understood through its effects on motion. This unseen matter helps determine how galaxies form and how they hold together. Without it, the visible stars alone would not remain bound in their observed patterns. Galaxies depend on both what shines and what does not, working together within the same gravitational framework. Across the universe, galaxies repeat these structures again and again. Spiral forms appear in distant regions, much like those nearby. Clusters show similar arrangements across enormous distances. This repetition reflects the consistency of physical laws, applied over vast scales and long durations. As space continues to expand, galaxies slowly drift farther apart on the larger scales. Still, within their local environments, gravity remains effective. Groups stay together. Clusters persist. The universe balances expansion and attraction at the same time. allowing structure to exist within change. There is no need to picture every galaxy or imagine their full number. It is enough to sense that space is populated by these vast, steady systems, each carrying countless stars within them, each moving quietly through the larger structure of the universe. Galaxies do not hurry. They follow paths shaped over billions of years, adjusting gradually as space stretches around them. Within their slow motion, stars are born, shine, and fade, while the galaxy itself continues, holding their combined histories within its gentle orbit. Within the vast population of galaxies spread across space, there is one that serves as a familiar reference point. Our home galaxy is called the Milky Way. The Milky Way is a spiral galaxy, shaped like a broad, flattened disk, with a gentle central bulge. From above, its structure resembles a slowly turning pinwheel, with curved arms extending outward from the center. These arms are not rigid or sharply defined. They are regions where stars, gas, and dust are more densely gathered, following long, steady paths shaped by gravity. The Milky Way is large. From one side of the disk to the other, it measures about 100,000 light-years across. Light traveling at its constant speed would take 100,000 years to cross from edge to edge. This distance exists entirely within a single galaxy, one of hundreds of billions spread throughout the observable universe. Inside this wide disk, stars orbit the galactic center at different distances and speeds. Their motion is slow and persistent, guided by gravity acting across immense spans. A single orbit around the center of the Milky Way can take hundreds of millions of years to complete. These paths repeat steadily, forming the long-lived structure of the galaxy itself. Our solar system is located within this disk, positioned about 2/3 of the way out from the center. It does not sit near the middle, nor at the outer edge. Instead, it occupies a quiet region between the denser inner areas and the thinner outer reaches. From this position, the Milky Way appears as a soft band of light stretching across the night sky, formed by countless distant stars blending together. Even from within the galaxy, its full shape is difficult to see directly. Dust and gas scattered throughout the disk absorb and scatter light, obscuring distant regions. Because of this, much of what is known about the Milky Way comes from careful observation across many forms of light, each revealing different layers of its structure. The Milky Way contains hundreds of billions of stars. Some are young and bright, surrounded by clouds of gas. Others are old and faint, having long since settled into quieter stages of existence. These stars are not evenly spaced. They cluster in spiral arms, gather near the central bulge, and thin out toward the outer edges of the disk. Between the stars lies interstellar space, filled with thin clouds of gas and dust. Though sparse, this material plays an essential role. It becomes the raw substance from which future stars form, circulating slowly through the galaxy over long spans of time. Nothing remains fixed. Matter moves, settles, and redistributes, guided by gravity and motion. The Milky Way also contains a large amount of matter that does not emit light. This unseen component extends well beyond the visible disk, forming a wide halo around the galaxy. Its presence helps hold the galaxy together, influencing how stars move and how the disk maintains its shape. Without this unseen mass, the Milky Way would not remain stable in the form we observe. Despite its size, the Milky Way is only one galaxy among many. It is not unusually large or unusually small. It follows the same physical rules as countless others scattered across space. Its structure, motion, and long-term behavior reflect patterns that repeat throughout the universe. From within the Milky Way, distances feel immense. Yet when placed among the full population of galaxies, it becomes part of a much larger arrangement. The galaxy moves along with nearby companions, participating in broader motions shaped by gravity and the expansion of space itself. As you rest with this idea, there is no need to imagine the galaxy in full detail. It's enough to sense its slow rotation, its wide disk, and its steady presence within a universe filled with similar systems. The Milky Way holds countless stars, countless histories, and long, patient motion, all unfolding without urgency. It is a quiet structure, moving through expanding space, carrying its stars gently along as it continues its long journey. Within galaxies like the Milky Way, new stars continue to form. This process begins in vast clouds of gas and dust called nebulae. These clouds drift quietly through space, spreading across many light years. They appear faint and diffuse with no sharp edges or clear boundaries. Inside them, matter is thinly distributed, yet abundant enough to shape what comes next. Over long spans of time, gravity begins to act. Small variations in density within a nebula cause material to gather slowly. Where gas and dust become slightly more concentrated, attraction increases. Particles draw closer together, not through forceful motion, but through gradual accumulation. This gathering continues, layer by layer, across thousands or millions of years. As material collects, the growing region becomes denser and warmer. Pressure increases at the center, and motion becomes more organized. The surrounding cloud continues to supply material, feeding the forming structure. At this stage, the process remains quiet and hidden, taking place deep within the nebula, where light struggles to escape. Eventually, the central region becomes hot enough for nuclear fusion to begin. Fusion is the process by which smaller atomic nuclei combine to form larger ones. When this happens in the core of a forming star, energy is released. This energy moves outward as light and heat, balancing the inward pull of gravity. When this balance is established, a new star begins to shine. The star's light marks the transition from gathering to sustained existence. What was once a cold, dark region becomes a steady source of energy. The surrounding nebula may glow faintly as the star's light illuminates nearby gas and dust, revealing shapes and structures that were previously hidden. Star formation does not happen all at once. Nebulae often give rise to many stars over extended periods. Some form in clusters, sharing a common origin within the same cloud. Others emerge more gradually, spaced across the nebula's broad extent. Each follows a similar path, shaped by gravity and the conditions of its environment. Not all forming stars are the same. The amount of material gathered during formation influences the star's size, temperature, and future behavior. Some stars grow large and luminous, while others remain smaller and dimmer. These differences are established early, long before the star settles into a steady state. The energy released by newly formed stars also affects their surroundings. Light and heat can disperse nearby gas, slowing or redirecting further formation. In this way, star birth shapes its own environment, gently changing the cloud from which it emerged. Despite these interactions, the overall process remains gradual. There are no sudden transitions. Gravity gathers material. Fusion begins when conditions allow. Light spreads outward. Each step follows from the last, guided by physical rules that operate the same way across the universe. Stars continue to form in galaxies today, just as they have for billions of years. Some nebulae visible in the night sky are active regions of star birth, while others remain quiet, holding their material without forming new stars for long periods. Both states are natural parts of the galactic cycle. As stars form, they become part of the larger structure of the galaxy. They join existing populations, moving along steady paths shaped by gravity. Over time, their light contributes to the glow of spiral arms and clusters, adding to the visible patterns seen from great distances. As you rest with this idea, there is no need to imagine the full complexity of the process. It's enough to sense clouds drifting, material gathering, and light beginning slowly from within. Star birth is not hurried. It unfolds patiently, following conditions that take time to develop. Within the Milky Way and countless other galaxies, these quiet beginnings continue, shaping the universe one star at a time, without announcement or urgency, simply as part of how matter organizes itself over long spans of time. Once a star begins to shine, it enters a long period of steady existence. This stage is often the longest part of a star's life. During this time, the star maintains a balance between two opposing processes. Gravity continues to pull matter inward, while the energy released by nuclear fusion pushes outward. When these forces remain balanced, the star holds its shape and shines at a consistent level. Stars vary widely in how long they remain in this stable state. Some stars are large, bright, and intense. They burn through their fuel quickly, releasing vast amounts of energy over relatively short spans of time. Others are smaller and dimmer, using their fuel slowly and steadily. These smaller stars can remain active for trillions of years, far longer than the current age of the universe. The size of a star plays a major role in determining its lifespan. Larger stars have more fuel, but they also consume it at a much faster rate. Smaller stars begin with less fuel, yet they use it carefully, allowing them to shine for extraordinarily long periods. This difference is established early, based on how much material the star gathered during formation. Color provides another clue. Hotter stars tend to shine with a bluish or white light, while cooler stars appear more red or orange. These colors reflect surface temperature and energy output. Over time, stars may change color slightly as their internal conditions evolve, but the process unfolds gradually. Our Sun is considered a medium-sized star. It is neither among the largest nor the smallest. Its energy output is steady, and its fuel consumption is balanced. This allows it to remain stable for billions of years, providing a consistent source of light and warmth to its surrounding system. The Sun is about 4.6 billion years old. It has already completed many orbits around the center of the Milky Way and continues to follow the same broad path it has maintained for much of its existence. In cosmic terms, the Sun is roughly middle-aged, with a long future still ahead of it. Across the galaxy, stars exist at every stage of their lifespan. Some have only recently begun to shine. Others have been stable for vast spans of time. Still others are nearing the end of their fuel supply. From a distance, these different stages blend together, creating the soft glow that fills galaxies and spiral arms. Stars do not all change in the same way as they age. Smaller stars gradually dim as fusion slows, transitioning gently without dramatic shifts. Larger stars undergo more pronounced changes, redistributing their material over wide regions of space. These outcomes depend on mass and internal structure, following physical rules that remain consistent throughout the universe. Even when stars change form, their material does not disappear. Elements created through fusion remain part of the universe, ready to become part of future systems. In this way, a star's lifespan contributes to a much longer cycle of matter, extending far beyond its own period of light. Time moves differently for stars than it does for human experience. A change that seems slow from one perspective may represent a significant transition over millions or billions of years. Stars follow these timescales naturally, without acceleration or delay, simply responding to the conditions within their cores. When you look at the night sky, you are seeing stars of many different ages at once. Some began shining long before Earth existed. Others formed more recently. Their light arrives together, layered across time, creating a sky that holds many stages of stellar existence in a single view. As you rest with this idea, there is no need to compare durations or imagine the full length of stellar lifespans. It's enough to sense that stars persist for a very long time, each following its own steady path from formation to transformation. Stars do not measure their own time. They do not hurry through their existence or linger beyond it. They simply follow the gradual use of fuel and the balance of forces that sustain them. Across the universe, countless stars continue shining, dimming, and changing form, each contributing to a larger pattern that unfolds slowly, shaped by gravity, fusion, and time itself. Among the many stars spread across the Milky Way, there is one that serves as a steady point of reference. The Sun is a medium-sized star. It does not belong to the largest or brightest group of stars in the galaxy, nor is it among the smallest or faintest. Its size and energy output place it near the middle of the wide range of stellar types. This balance allows the Sun to shine steadily for long spans of time, maintaining a stable presence within its surrounding system. The Sun formed about 4.6 billion years ago, emerging from a cloud of gas and dust, much like countless other stars throughout the galaxy. Since then, it has remained in a long phase of stability, producing energy through nuclear fusion in its core. Hydrogen atoms combine to form helium, releasing light and heat that travel outward through the Sun and into space. This energy spreads in all directions, filling the surrounding region with warmth and illumination. At the scale of the galaxy, the Sun's output is modest. It does not dominate its surroundings. It simply contributes its share of light to the broader glow of the Milky Way, one star among hundreds of billions. The Sun follows a slow path around the center of the galaxy. A single journey around the Milky Way takes hundreds of millions of years. Over its lifetime so far, the Sun has completed only a small number of these long orbits, moving calmly through the galactic disk along with nearby stars. From its position in the galaxy, The Sun resides in a relatively quiet region. It is not near the dense central bulge, where stars crowd together more closely. It is also not at the far edge, where stars become more sparse. Instead, it occupies a balanced location within the disk, participating in the galaxy's overall motion without standing apart from it. The Sun's size influences how it will change over time. Because it is neither extremely large nor extremely small, its fuel will be used at a measured pace. This allows the Sun to remain stable for billions of years, providing a consistent source of energy rather than a brief burst of brightness. This steadiness is not unique. Many stars throughout the universe share similar properties. The Sun does not represent a special category of star. It follows the same physical rules as others like it, shaped by gravity, fusion, and time in the same way. The light produced by the Sun travels outward at a constant speed. It takes about 8 minutes to reach Earth, crossing space without slowing or dispersing. During that journey, the light remains unchanged by distance alone, carrying information about the Sun's surface and energy output from the moment it was released. Beyond Earth, the Sun's light continues outward, passing through the solar system and into interstellar space. Eventually, it blends with the background light of the galaxy, becoming indistinguishable from the countless other sources that fill the Milky Way. In this way, the Sun's light becomes part of a much larger field of energy moving through space. The Sun also holds its surrounding system together through gravity. Objects orbit steadily around it, following paths shaped by its mass. These motions are predictable and persistent, repeating across long spans of time. Nothing in this system moves quickly or abruptly. Each path unfolds gradually, guided by the same forces that shape motion throughout the universe. As the Sun continues its long existence, its internal processes will change slowly. Over very long periods, the balance between gravity and fusion will shift, leading to gradual transformation. These changes remain far in the future and unfold across timescales that extend well beyond human experience. For now, the Sun remains stable, shining quietly within a galaxy filled with similar stars. It does not mark the center of anything beyond its immediate surroundings. It participates in the same patterns of motion, energy, and time that govern all stars. As you rest with this idea, there is no need to hold the Sun apart from the universe around it. It is part of a continuous field of stars, each shining according to the same principles, each following long, steady paths through space. The Sun is simply one example of how stars exist across the universe. Medium-sized, long-lived, calm in its output, moving slowly through a galaxy that itself moves through expanding space. Around many stars, material continues to organize itself long after the star has formed. When a star is born, not all of the surrounding gas and dust becomes part of it. Some of this material remains in a broad, rotating disk encircling the young star. Over time, particles within this disk begin to collide gently, sticking together and forming larger structures. This is how planets begin. The process unfolds slowly. Small grains combine into larger pieces. These pieces gather more material as they move through the disk, gradually increasing in size. Gravity plays a steady role, guiding motion and helping matter collect without sudden change. Over millions of years, these growing bodies become recognizable planets. Not all planets form in the same way or end up with the same properties. Some develop solid surfaces built from rock and metal. Others gather thick layers of gas or ice, becoming much larger and less dense. The final outcome depends on distance from the star, available material, and the conditions within the disk during formation. Distance matters because it affects temperature. Regions closer to a star are warmer, allowing only certain materials to remain solid. Farther out, cooler conditions allow ices and gases to persist. These temperature differences help shape what kinds of planets can form and where they are likely to appear. Planets settle into paths called orbits, following steady routes around their star. These paths are shaped by gravity and motion, rather than direction or intent. Some orbits are nearly circular. Others are more elongated. Once established, these motions remain consistent over long periods, repeating calmly again and again. Many stars are believed to host planetary systems. Observations have revealed thousands of exoplanets orbiting stars beyond the Milky Way. These discoveries show that planets are not rare exceptions. They appear to be a natural result of star formation, emerging wherever conditions allow disks of material to persist. Exoplanets display a wide range of characteristics. Some are larger than Jupiter, while others are smaller than Earth. Some orbit very close to their stars, completing a full circuit in just days. Others follow wide paths that take many years to complete. These differences reflect the variety of environments in which planets form. Some planetary systems contain many planets, arranged in layered structures with inner and outer regions. Others appear simpler, with fewer bodies or more widely spaced orbits. Each system reflects a unique history shaped by motion, gravity, and gradual change over time. Planets do not exist in isolation. They often share their systems with smaller objects such as moons, rings, and debris fields. These elements move together, guided by gravity and mutual influence. Even the smallest particles follow predictable paths, contributing to the overall structure of the system. Light from a star interacts with its planets in subtle ways. Planets do not emit light of their own. They become visible by reflecting or absorbing the light that reaches them. This reflected light carries information about a planet's surface and atmosphere, allowing distant observers to infer properties without direct contact. As planets continue along their orbits, their positions change slowly and regularly. These motions create repeating patterns that can persist for billions of years. Stability arises not from stillness, but from continuous movement that remains balanced and orderly. Across the universe, planetary systems exist around stars of many types. Some orbit small, dim stars. Others surround large, bright ones. The presence of planets does not depend on a star being unusual or exceptional. It follows naturally from the presence of leftover material and the steady influence of gravity. As you rest with this idea, there is no need to imagine every planet or every orbit. It is enough to sense disks forming, matter gathering, and paths settling into place. Stars become centers not by command, but by gravity acting patiently over time. Planets form, systems take shape, motion continues. Across galaxies filled with stars, countless planetary systems follow their steady courses. each unfolding quietly within the larger structure of the universe, carried forward by the same physical rules that guide everything else. Between stars and planets, space appears quiet and open. From a distance, it looks empty. Dark regions stretch between points of light, giving the impression that nothing exists there at all. Yet this appearance is shaped by scale and visibility, not by absence. Even the most open regions of space contain substance. Space is filled with particles. These particles are spread very thinly, far more sparse than anything encountered on Earth. In the emptiest regions, there may be only a few atoms within a volume as large as a room. Still, those atoms are present, moving gently and interacting according to the same physical rules that govern matter everywhere else. Alongside particles, space contains radiation. Light travels through space continuously, crossing vast distances without sound or resistance. Other forms of radiation move as well, carrying energy through regions that appear dark to the eye. This movement never stops. Even in places far from stars, energy continues to pass through quietly. Space also contains fields. Magnetic fields thread through galaxies, shaped by motion and charged particles. These fields are weak compared to those near planets or stars, yet they extend across enormous distances. They influence how particles move and how energy flows, adding subtle structure to regions that seem uniform at first glance. The density of matter in space is extremely low. Compared to Earth's atmosphere, even the most populated regions between stars contain almost nothing. Yet when spread across the immense volume of the universe, this thin distribution adds up. Over time, it becomes enough to shape motion, form clouds, and contribute to the slow organization of matter. Dust grains drift through space as well. These grains are tiny, often smaller than a grain of smoke. They scatter light, absorb energy, and gradually move through interstellar regions. Though individually insignificant, together they influence how galaxies appear and how stars form. Gas fills much of the space between stars. This gas is mostly hydrogen, with smaller amounts of helium and trace elements. It moves gently, shaped by gravity, pressure, and nearby energy sources. Over long periods, gas may gather into clouds, become part of nebulae, or remain spread thinly across wide regions. Even the most open areas of space are part of a continuous environment. There are no sharp transitions from something to nothing. Density changes gradually. Matter thins out, energy becomes less concentrated, and light grows faint, but presence remains. This quiet content of space plays an important role. Particles interact, radiation passes through, fields guide motion. Together, these elements shape how stars form, how galaxies evolve, and how energy moves across the universe. Space is not a backdrop. It participates, even when it appears still. Because space is so sparse, motion within it feels gentle. Particles travel long distances without frequent interaction. Light moves freely. Energy spreads gradually. These conditions allow processes to unfold over long spans of time without disruption. From within a planetary system, space may feel vast and open. From the perspective of a galaxy, it becomes a medium through which stars and systems move. From the largest scale, it is part of the structure that connects everything, holding matter and energy together within the same framework. As you rest with this idea, there is no need to picture every particle or trace each path. It's enough to sense that space is quietly filled, not crowded, but present. Substance exists even where light does not linger. The universe does not alternate between fullness and emptiness. It transitions smoothly, with density fading rather than disappearing. Matter thins, energy spreads, fields extend gently across distance. Within this setting, stars shine, planets orbit, and galaxies drift, all embedded within space that remains active in subtle ways. Even where nothing seems to happen, the quiet movement of particles and energy continues. Space holds these processes without comment. It allows motion without resistance and change without disturbance. It remains present everywhere, forming the environment in which everything else unfolds. As we move through the universe, light shows only part of what exists. Galaxies shine with the combined glow of billions of stars, yet their visible matter tells only a fraction of the story. When astronomers study how galaxies move and hold together, the light alone is not enough to explain what they observe. Something else must be present, shaping motion without announcing itself. This unseen component is called dark matter. Dark matter does not emit light. It does not reflect light. It does not glow when heated in the ways familiar forms of matter do. Because of this, it cannot be seen directly, even with powerful instruments. Its presence is known through influence, rather than appearance. The primary way dark matter reveals itself is through gravity. Galaxies rotate in ways that cannot be explained by their visible stars and gas alone. Stars far from a galaxy's center move faster than expected, as if additional mass were present, holding them in place. Without this unseen mass, galaxies would slowly drift apart, rather than remaining intact. Dark matter provides this added gravitational structure. It forms extended halos around galaxies, reaching far beyond the visible stars. These halos help stabilize galactic disks and influence how galaxies interact with one another. Though invisible, dark matter plays a central role in shaping the structure of galaxies across the universe. On larger scales, dark matter affects how galaxies gather into groups and clusters. Its gravitational pull guides matter into long-lived arrangements, helping shape the large-scale patterns that stretch across space. Without dark matter, the universe would look very different, with fewer stable structures and less organization. Dark matter does not behave like ordinary matter. It does not clump into stars or planets. It passes through space without forming familiar objects. It interacts very weakly with other forms of matter, making it difficult to detect directly. Yet its gravitational presence is consistent and measurable. Because dark matter cannot be observed directly, scientists infer its existence by studying motion. They examine how stars orbit within galaxies, how galaxies move within clusters, and how light bends as it travels through space. In each case, the observed motion points to more mass than can be seen. This method of understanding does not rely on speculation. It relies on repeated measurement and consistent patterns. Wherever galaxies form and move, the same gravitational effects appear. Dark matter behaves the same way across vast distances, suggesting it is a fundamental component of the universe. Most of the matter in the universe is believed to be dark matter. Ordinary matter, the kind that forms stars, planets, and living things, makes up only a small fraction of the total. The rest exists quietly, shaping motion and structure without becoming visible itself. Dark matter does not replace ordinary matter. It works alongside it. Visible matter gathers within the gravitational framework that dark matter provides. Stars form where dark matter has helped concentrate gas. Galaxies follow paths influenced by dark matter's distribution. In this way, dark matter acts like an underlying framework. It does not dominate through brightness or activity. It supports structure by presence alone, allowing visible matter to settle into long-lasting patterns. As you rest with this idea, there is no need to imagine dark matter as something strange or unfamiliar. It does not behave unpredictably. It follows the same gravitational principles that apply everywhere else. Its difference lies only in how it interacts with light. The universe contains much that does not shine. Dark matter is part of this unseen majority, steady and consistent, guiding motion quietly across vast distances. Even though it cannot be seen, dark matter helps hold galaxies together, shape clusters, and define the large-scale arrangement of matter in the universe. It remains present everywhere structure exists, influencing the universe through gravity alone. Within this quiet framework, galaxies continue to turn, stars continue to shine, and space continues to expand, all supported by forces that do not require visibility to be effective. Alongside matter, both visible and unseen, the universe also contains energy that affects how space itself behaves. This energy is called dark energy. Dark energy does not form structures the way matter does. It does not gather into clouds, stars, or galaxies. Instead, it is associated with the expansion of space. Wherever space exists, dark energy is present as well, influencing how distances change over time. As the universe expands, galaxies move farther apart. This motion is not caused by galaxies pushing away from one another. It arises because space itself is stretching. Dark energy is linked to this stretching, gently affecting the large-scale behavior of the universe as a whole. Observations show that expansion is not slowing down. Instead, it has been gradually increasing over long spans of time. This change is subtle and becomes noticeable only when distances are measured across enormous scales. Dark energy helps explain why expansion continues in this steady way. Unlike matter, dark energy does not clump or concentrate. It remains spread evenly throughout space. This uniform presence means that its influence becomes more noticeable as space grows larger. As the universe expands, there is simply more space for dark energy to occupy, and its effect becomes more pronounced. Dark energy does not act against gravity in a simple sense. On smaller scales, gravity remains dominant. Stars stay bound within galaxies. Galaxies remain grouped in clusters. Dark energy becomes significant only across the largest distances, where gravity's influence weakens and space itself plays a larger role. Because of this balance, the universe can contain both stable structures and ongoing expansion at the same time. Galaxies hold together locally, while the space between distant systems continues to widen. These two processes coexist without conflict, each operating where it is most effective. Dark energy makes up most of the universe's total energy content. Ordinary matter and dark matter together account for a smaller portion. This does not mean that dark energy overwhelms everything else. It simply reflects how energy and matter are distributed across the vast scale of the universe. Dark energy does not have a temperature, shape, or surface. It does not emit light or absorb it. Its presence is inferred from how space changes, rather than from anything that can be seen directly. Like dark matter, it is understood through careful observation and consistent patterns. The influence of dark energy is steady. It does not fluctuate rapidly or behave erratically. Its effect unfolds slowly, shaping the universe across billions of years. Distances increase. Space becomes more expansive. Structures remain where gravity holds them, while separation grows between distant regions. Because dark energy is evenly distributed, it does not create preferred directions or locations. Expansion looks the same in every direction on the largest scales. No region of space is singled out as a center or origin. The universe grows uniformly, guided by the same underlying conditions everywhere. This evenness allows scientists to describe the universe using simple, consistent principles. The same relationships apply regardless of location. Expansion proceeds in the same general way across all observable regions, reflecting the uniform presence of dark energy throughout space. As the universe continues to expand, dark energy remains part of that process. It does not diminish as space grows. Instead, it continues to influence how distances change over time, contributing to a future in which galaxies become more widely separated from one another. These changes do not happen quickly. They unfold across spans of time that far exceed human experience. From moment to moment, nothing appears different. From one lifetime to the next, the universe seems unchanged. Only when viewed across immense durations does the effect of dark energy become clear. As you rest with this idea, there is no need to imagine expansion as movement or force. It is enough to sense space becoming more spacious, distances gently increasing, and the universe continuing its long, even development. Dark energy does not require observation to act. It does not respond to presence or absence. It simply remains part of space itself, shaping the overall behavior of the universe quietly and consistently. Within this expanding framework, matter continues to gather where gravity allows. Stars continue to shine for their long lifespans, and galaxies follow their slow paths through space. Expansion carries on in the background, steady and uniform. As we move forward, this expansive influence helps set the stage for the largest patterns in the universe, where matter traces vast networks across space, forming structures that stretch far beyond individual galaxies. Across the largest distances that can be observed, matter in the universe does not spread evenly. Instead, it arranges itself into vast patterns that stretch across hundreds of millions of light years. These patterns are subtle and expansive, formed gradually as gravity guides matter over immense spans of time. Together, they create what is known as the cosmic web. The cosmic web is made of long filaments of matter. These filaments connect clusters of galaxies, forming thread-like structures that span great distances through space. Along them, galaxies gather more densely, drawn together by gravity acting steadily over billions of years. The filaments are not narrow or sharply defined. They are broad regions where matter is slightly more concentrated than its surroundings. Between these filaments lie wide regions called voids. Cosmic voids contain very few galaxies. They are not completely empty, but they are far less dense than the filaments that surround them. These quiet regions can stretch for tens or even hundreds of millions of light years, creating vast open spaces between the brighter, more populated areas of the universe. The largest known structures in the universe emerge from this arrangement. Filaments intersect at dense nodes, where clusters of galaxies gather. From these nodes, matter extends outward along multiple filaments, forming a connected network that spans the observable universe. This structure did not appear suddenly. In the early universe, matter was distributed more evenly. Over time, small differences in density grew under the influence of gravity. Regions with slightly more matter attracted more material, becoming denser. Regions with slightly less matter gradually emptied out. This slow process, repeated across enormous distances, gave rise to the web-like arrangement seen today. Dark matter plays a central role in shaping this structure. Because dark matter interacts through gravity, it helps guide ordinary matter into filaments and clusters. Visible galaxies form along these gravitational pathways, tracing the underlying structure created by unseen mass. What can be seen through telescopes reflects a deeper framework that extends far beyond visible light. The cosmic web is not static. Galaxies continue to move within it. Clusters slowly change shape. Filaments evolve as matter flows along them. These changes happen gradually, guided by gravity and the expansion of space, unfolding across timescales far longer than human history. Even as the universe expands, the web remains coherent. Expansion increases the distances between distant regions, yet gravity continues to hold matter together locally. Filaments stretch, clusters drift, and voids widen gently, all within the same overarching structure. From within a single galaxy, the cosmic web cannot be seen directly. Its scale is too large. Its features are too spread out. It becomes visible only when many galaxies are observed together, allowing patterns to emerge through careful measurement and long observation. Maps of the universe reveal these patterns clearly. When plotted across space, galaxies trace out long chains and walls surrounding wide, quiet voids. The result resembles a three-dimensional network, extending in all directions without a preferred orientation or central point. This organization reflects the consistency of physical laws across space. Gravity behaves the same way everywhere it has been measured. Matter responds in predictable ways. Over time, these simple rules give rise to complex, far-reaching structures without the need for design or direction. The cosmic web also helps explain why galaxies appear where they do. Galaxies form more readily where matter is already concentrated. Along filaments, gas flows inward, supporting star formation and long-term structure. In voids, matter remains sparse and fewer galaxies develop. This uneven distribution is not a flaw or imbalance. It is a natural outcome of matter responding to gravity over long spans of time. The universe does not seek uniformity. It follows the paths shaped by its own physical properties. As you rest with this idea, there is no need to picture the full web in detail. It is enough to sense connection across distance. Threads of matter stretching through space. Wide regions of quiet openness in between. Structure and openness existing together. The universe, on its largest scales, is neither crowded nor empty. It is organized gently, with matter flowing along extended paths and gathering where conditions allow. The cosmic web provides a framework that holds galaxies within a broader pattern, linking them across distances too large to feel directly. Within this vast network, stars shine, galaxies turn, and space continues to expand, all unfolding within a structure shaped by gravity and time, steady and enduring. Prior to galaxies forming their spirals, before stars began to shine, the universe existed in a very different state. In its earliest period, the universe was hot, dense, and filled with energy. Matter and radiation were closely coupled, interacting constantly. Space was smaller than it is now, and everything within it was much closer together. Light could not yet travel freely. Instead, it scattered repeatedly, absorbed and re-emitted by charged particles, never moving far before being redirected. As the universe expanded, it gradually cooled. Over time, conditions changed enough for charged particles to combine into neutral atoms. When this happened, light was no longer trapped. It was able to move freely through space for the first time. This moment marked the release of the universe's earliest freely traveling light. That light still exists today. It fills all of space as a faint background glow known as cosmic background radiation. This radiation is not concentrated in one direction or location. It arrives evenly from every part of the sky, surrounding Earth completely. No matter where instruments are pointed, the same soft signal is detected. This background light is remarkably uniform. Its temperature is just a few degrees above absolute zero, reflecting how much the universe has cooled since its early state. The warmth is subtle and constant, spread evenly across space. It does not fluctuate rapidly or sharply. It remains steady, a quiet remnant of a much earlier time. Although it is faint, this radiation carries an extraordinary amount of information. It provides a direct record of the universe when it was very young, long before stars or galaxies existed. Tiny variations within this background reveal how matter was distributed at that time. These small differences eventually grew into the large-scale structures seen today, including galaxies, clusters, and the cosmic web. The background radiation acts like a snapshot, preserved across time. As the universe expanded, the light stretched along with space. Its wavelength increased, shifting it out of the visible range and into longer wavelengths. Though invisible to human eyes, it remains detectable with sensitive instruments designed to measure subtle energy differences. Everywhere space exists, this background light is present. It does not belong to any star or galaxy. It does not originate from a particular region. It comes from all directions equally, reflecting a time when the universe itself was the source of light. In this sense, it is the most widespread signal in existence. This radiation confirms that the universe has changed over time. Its existence shows that the universe was once warmer and denser than it is now. As space expanded, energy spread out and cooled. What remains today is a quiet echo of that early condition, still traveling through space billions of years later. The background radiation does not fade with distance. Because it fills all of space, it reaches observers everywhere in the same way. No matter how far one travels, the background remains. It is part of the environment of the universe itself, present between galaxies, within clusters, and across voids. Despite its significance, the background radiation is not intrusive. It does not overwhelm other signals. It does not dominate the night sky. It exists gently in the background, detectable only through careful measurement. For most of human history, it went unnoticed, quietly passing through Earth long before instruments were capable of sensing it. This first light links the present universe to its earliest moments. Stars, planets, and galaxies formed later, building complexity over time. The background radiation predates all of these structures. It comes from an era before the universe had shape in the way it does now, before matter gathered into recognizable forms. As you rest with this idea, there is no need to imagine the early universe vividly or in detail. It is enough to sense continuity. Light released long ago still moves through space. Expansion stretches it gently. Time carries it forward. The universe does not erase its past. It carries it quietly. The first light continues to travel, filling every region of space with a faint, even presence. It remains as a reminder that the universe has a history, one that unfolds gradually and leaves traces that persist across billions of years. As we move forward, this gentle cooling and spreading of energy becomes part of the universe's long-term settling, shaping how matter and temperature change over time, guiding the universe toward broader, quieter conditions. After the universe released its earliest freely traveling light, it continued to change in a quiet and consistent way. Expansion did not stop. Space kept stretching, and as it did, energy spread out across a growing volume. This spreading caused temperatures to decrease gradually. What was once intensely hot became warm, and what was warm continued to cool step by step over vast spans of time. Cooling in the universe does not happen suddenly. It unfolds as a natural result of expansion. As space grows larger, the same amount of energy occupies more room. With more space available, energy becomes less concentrated. Temperatures decrease not because heat disappears, but because it is shared across a wider expanse. In the early universe, temperatures were high enough to prevent stable structures from forming. Particles moved rapidly, colliding frequently. Under these conditions, complex forms could not persist. As cooling progressed, motion slowed slightly, and interactions became less intense. This gradual change allowed new forms to emerge. As temperatures dropped, particles were able to combine into atoms. Protons and electrons joined together, forming neutral hydrogen and helium. These were the first stable elements to exist in the universe. Their formation marked an important transition, allowing matter to persist in a more organized state. Hydrogen and helium became the primary building blocks of everything that followed. They filled space in vast quantities, spreading evenly as the universe continued to expand. Heavier elements did not yet exist. They would form much later, inside stars, through long processes of fusion. The cooling universe also became more transparent. Once atoms formed, light was able to travel freely without being scattered constantly. This transparency allowed energy to move across space with greater ease, contributing to further cooling over time. Light stretched as space expanded, lowering its energy gradually and consistently. Temperature differences across the universe were small. Even early on, conditions were remarkably uniform. Slight variations existed, but large extremes were rare. This evenness allowed matter to evolve in a balanced way, avoiding sharp contrasts or unstable conditions across wide regions of space. As expansion continued, the universe moved toward cooler and calmer states. Gas thinned, energy spread out, motion slowed slightly as distances increased. None of this required direction or coordination. It followed directly from the physical relationship between space, energy, and time. Cooling did not eliminate activity. Stars would still form later. Galaxies would gather. Motion would continue. Cooling simply set the conditions under which these processes could occur. By lowering temperatures, the universe allowed matter to organize itself into lasting structures rather than remaining in constant motion. Even today, the universe continues to cool. The faint background radiation still present throughout space carries a temperature just a few degrees above absolute zero. This value reflects billions of years of expansion and energy spreading. It is a quiet measure of how far the universe has come from its early state. This cooling trend unfolds slowly. From one moment to the next, nothing seems to change. From one lifetime to the next, temperatures remain effectively the same. Only when viewed across enormous spans of time does the shift become noticeable. The universe does not rush toward lower temperatures. It arrives there gradually. Cooling affects how matter behaves on the largest scales. As energy becomes more diffuse, interactions become less frequent. Regions of space grow more separated. Structures persist where gravity holds them together, while the space between them becomes broader and quieter. Despite this, physical laws remain unchanged. The same principles governing motion, energy, and matter continue to apply everywhere. Cooling does not alter these rules. It simply changes the conditions under which they operate. Gravity still gathers matter. Light still travels. Expansion continues. As the universe cools, it becomes increasingly stable. Large-scale changes occur less often. The pace of visible transformation slows. The universe trends toward states where activity is spread out rather than concentrated, where energy is present but gentle. As you rest with this idea, there is no need to imagine specific temperatures or measure degrees. It is enough to sense warmth fading into cooler states over immense time. Energy spreading thinly across expanding space, and matter settling into patterns that persist. Cooling is not an ending. It is a continuation of the same process that has guided the universe from its earliest moments. Expansion, energy spreading, and gradual change all move together, shaping the universe's long development. As the universe cooled and matter settled into stable forms, new processes became possible. Hydrogen and helium filled space, drifting quietly through expanding regions. These simple elements were enough to form stars, but they were not enough to create the full range of matter seen today. The variety of elements found throughout the universe required time, structure, and sustained energy. Stars provide those conditions. Inside the core of a star, pressure and temperature reach levels high enough to allow nuclear fusion to occur. Atoms combine in carefully ordered steps, forming heavier elements from lighter ones. This process unfolds gradually, governed by balance rather than force, and it continues for as long as the star remains active. Fusion begins with hydrogen. In the core of a star, hydrogen atoms combine to form helium, releasing energy as light and heat. This energy supports the star against gravitational collapse and allows it to shine steadily. Over long periods, as hydrogen becomes less abundant in the core, stars begin forming heavier elements in successive stages. Helium can combine to form carbon. Carbon can lead to oxygen. In larger stars, fusion continues through a sequence of steps that create elements such as neon, magnesium, silicon, and iron. Each stage requires specific conditions of pressure and temperature, achieved only within stellar interiors. These processes take time. Elements are not created all at once. They form slowly, layer by layer, over millions or billions of years. Smaller stars produce fewer elements, stopping at lighter ones. Larger stars can create a wider range, building up complex internal structures before their fuel supply changes. When stars reach later stages of their existence, their material does not vanish. Instead, it returns to space. Some stars release their outer layers gently, allowing gas enriched with newly formed elements to drift outward. Other stars scatter their material more widely, distributing elements across surrounding regions. In both cases, the matter that once formed the star becomes part of the wider universe again. This returned material mixes with interstellar gas and dust. Over time, it becomes part of new clouds, new nebulae, and eventually new stars and planets. Each generation builds upon the material of those that came before. The universe does not discard its matter, it circulates it. Elements essential to planets and life are created through this long process. Carbon, oxygen, nitrogen, and iron all originate within stars. They are not present in large quantities at the beginning of the universe. They emerge gradually as stars form, shine, and change, contributing their material back to space. This means that matter carries a history. Atoms found in planets were once part of stars. Atoms within living things were formed through stellar processes long before they became part of any biological system. They traveled through space, gathered into new structures, and eventually became part of complex arrangements. This continuity extends across immense spans of time. Stars form from materials shaped by earlier stars. Each generation adds subtle differences, increasing the variety of elements available. Over billions of years, this gradual enrichment allows the universe to support more complex structures. The process remains steady and consistent. Stars follow the same physical rules wherever they form. Fusion proceeds in predictable ways. Material returns to space according to mass and structure. Nothing about this process requires intention or direction. It arises naturally from the conditions within stars. Galaxies act as environments where this circulation occurs. Stars form within them, release material, and contribute to the ongoing cycle. Gas flows through spiral arms. Clouds gather and disperse. Over long spans, galaxies become richer in heavier elements, shaping the kinds of planets and systems that can form. This gradual enrichment does not happen quickly. From one generation to the next, changes are subtle. Over many generations, the effects become significant. The universe builds complexity slowly, through repetition rather than acceleration. As you rest with this idea, there is no need to trace every transformation or follow each element's path. It is enough to sense continuity. Matter moves from stars to space and back again, carrying its history quietly forward. The universe is not made only of what exists now. It is made of what has passed through countless stars, shaped by fusion, returned to space and gathered again. Every solid surface, every gas cloud, and every distant planet reflects this long process of transformation. Stars do not simply shine. They change what matter can become. Through their long lifespans, they turn simple beginnings into richer material, allowing the universe to develop greater variety over time. This work continues wherever stars exist, shaping the substance of the universe gently and persistently. This circulation of matter sets the stage for even longer developments, where time itself becomes the dominant scale, and the universe continues toward quieter conditions, guided by the same steady physical processes. Time in the universe unfolds very differently than time in daily experience. On Earth, time is often measured in seconds, minutes, and years. These units are useful for daily life, but they represent only a very small portion of what time looks like across the universe. Cosmic processes operate on spans so long that individual moments blend together, forming slow, continuous change rather than distinct events. The universe itself is about 13.8 billion years old. This span includes everything from the release of the earliest light to the formation of stars, galaxies, and planets. Within this duration, countless processes have unfolded gradually, each guided by steady physical rules rather than rapid shifts. Time, at this scale, acts as a broad medium through which change flows smoothly. Earth has existed for only a small fraction of this cosmic time. Our planet formed long after the first stars began shining. Many stars visible in the night sky are far older than Earth itself. Some began their existence billions of years before the solar system formed and have continued shining steadily ever since. This means that the night sky contains many layers of age. When you look upward, you are seeing stars at different points in their long lifespans. Some are relatively young, having formed more recently from enriched clouds of gas. Others are ancient, carrying histories that stretch back toward the early universe. Their light arrives together, blending these different ages into a single view. Light plays a unique role in how time is revealed. Because light takes time to travel, it preserves moments from the past. When light reaches Earth, it carries information from the time it was released. In some cases, that release happened millions or billions of years ago. In others, it occurred more recently. Either way, light allows the universe's history to remain visible long after events have passed. Some stars visible today no longer exist. Their light continues to travel through space, arriving at Earth long after the stars themselves have changed form. This does not represent loss or absence. It reflects the persistence of light and the way time and distance work together. The universe carries traces of its earlier states forward naturally. At cosmic scales, time does not separate neatly into before and after. Instead, different moments coexist through the movement of light. Regions closer in space appear closer in time. Regions farther away appear younger, revealing earlier stages of development. The universe presents itself as a layered record rather than a single moment frozen in place. Stars follow their own extended timelines. Some burn through their fuel in millions of years. Others last for trillions, shining gently for durations far longer than the universe's current age. These differences arise from mass and structure, not from circumstance. Time moves through each star at a pace determined by its internal balance. From a cosmic perspective, change is gradual. Galaxies shift slowly within clusters. Clusters drift through larger structures. Expansion increases distances steadily over billions of years. None of this requires sudden transitions. It unfolds continuously, guided by gravity and the shape of space itself. This long view of time allows structures to persist. Galaxies maintain their forms for billions of years. Stellar populations evolve slowly. Matter circulates through generations of stars without being hurried. Time provides room for processes to complete naturally, without compression or acceleration. Even the universe's earliest moments remain connected to the present. The faint background radiation still traveling through space today carries information from a time before stars existed. Light released then continues moving now, linking distant past and present without interruption. Time does not erase these connections. It stretches them across space. As you rest with this idea, there is no need to measure or compare durations. Human experience does not need to match cosmic scale to be meaningful. Time in the universe simply follows its own pace, allowing change to unfold gently across immense spans. Nothing is lost by moving slowly. Everything that exists has room to persist. The universe does not hurry through its history. It allows stars to shine for billions of years. It allows galaxies to form and evolve gradually. It allows light to continue traveling long after its source has changed. Time provides the continuity that holds these processes together. Seen this way, time becomes a quiet presence rather than a pressure. It carries moments forward without demand, allowing the universe to change in ways that remain steady and consistent. As we continue, this vast sense of time sets the stage for another quiet feature of the universe, where motion continues everywhere, even in places where nothing can be heard. Throughout the universe, motion is constant. Stars travel along long paths within galaxies. Galaxies move within groups and clusters. Clusters shift within even larger structures. On every scale, matter follows trajectories shaped by gravity and the expansion of space. Yet despite all of this movement, the universe remains completely silent. Sound requires a medium to travel. On Earth, sound moves through air, water, or solid material. It depends on particles colliding and their passing vibrations along. In space, matter is spread extremely thinly. The gaps between particles are so wide that vibrations cannot propagate in the familiar way. As a result, motion in space produces no sound. This silence is not the absence of activity. Objects in space are always moving, even when they appear still. Planets follow steady orbits around stars. Stars circle the centers of galaxies. Galaxies drift relative to one another. These motions unfold continuously, guided by gravity acting across vast distances. Gravity shapes movement without noise. It pulls matter inward, curves paths, and governs long-term behavior without friction or resistance. There are no collisions that produce echoes, no vibrations that spread outward. Motion unfolds cleanly, guided by force alone rather than contact. Because there is no sound, movement in space does not announce itself. A star does not roar as it burns fuel. A galaxy does not rumble as it turns. Even the largest structures in the universe shift quietly, their motion detectable only through careful measurement of position and light. Light replaces sound as the primary messenger. Instead of carrying vibration, light carries information through electromagnetic waves. It moves freely through space, unaffected by the silence around it. Changes in motion, distance, and energy are revealed through shifts in light rather than through sound. This creates a universe where motion and quiet coexist. Energy flows, objects move, forces act, yet nothing breaks the stillness. From one moment to the next, the universe maintains a calm sensory environment, even as complex processes continue. This silence allows motion to persist without interruption. Without resistance from a medium, objects continue along their paths once set in motion. Orbits remain stable over long spans of time. Trajectories change only when influenced by gravity or interaction with other matter. Movement remains smooth and continuous. On the larger scales, galaxies orbit within clusters. These motions unfold over billions of years. From moment to moment, they are imperceptible. Over long durations, they shape the structure of the universe. Yet throughout this motion, silence remains complete. Even energetic events do not carry sound through space. Light and other forms of radiation spread outward, but no vibration accompanies them. Energy disperses without noise. Motion proceeds without disturbance. This quiet does not imply emptiness or inactivity. Particles move, fields extend, radiation travels, gravity shapes paths. All of these processes continue regardless of sensory experience. The universe does not rely on sound to function. As you rest with this idea, there is no need to imagine movement vividly. It is enough to sense motion happening everywhere, guided by steady forces, while silence remains absolute. Objects travel long distances without announcing themselves. Paths unfold smoothly without friction or resistance. The universe offers motion without noise, change without disturbance. In this setting, activity continues quietly, shaped by gravity and time rather than vibration. Stars move, galaxies drift, space expands. All of it happens without sound, allowing the universe to remain calm even as it changes. As we move forward, this quiet motion helps place our location within a larger arrangement, where groups of galaxies travel together through space, carried along by the same silent forces. Within the wide expanse of the universe, galaxies do not exist alone. They tend to gather into small collections, bound together by gravity and long-term motion. These collections form natural groupings where galaxies travel through space alongside one another, maintaining loose relationships over immense spans of time. The Milky Way is part of one such grouping. This collection is known as the local group. It contains a few dozen galaxies of varying sizes, spread across a region of space several million light-years wide. Some members are large spiral galaxies, while others are much smaller, containing fewer stars and less structure. Within the local group, galaxies follow slow paths influenced by gravity. They do not move quickly relative to one another. Instead, they drift gradually, maintaining their positions within the group for long periods. The space between them is vast, yet their shared motion reflects a subtle connection shaped by mass and distance. The Milky Way travels through space alongside its neighbors. These neighboring galaxies occupy different positions within the group, yet they remain linked by gravitational influence. Their motion unfolds across billions of years, allowing the group to persist as a recognizable structure rather than dispersing immediately into wider space. The local group itself is not isolated. It is part of a much larger arrangement called a supercluster. Superclusters are enormous regions where many galaxy groups and clusters gather, forming extended structures that span hundreds of millions of light years. Within these regions, gravity weaves together motion across great distances. Movement within a supercluster is extremely slow. From one moment to the next, nothing appears to change. From one lifetime to the next, positions remain effectively the same. Only when viewed across immense durations does the gradual shifting become apparent. These motions are measured not in years, but in billions of years. Despite this slow pace, the structure remains coherent. Groups remain associated. Clusters hold together. The larger framework persists even as space continues to expand. Gravity works quietly, guiding motion without compression or urgency, allowing systems to remain connected across long spans of time. The Milky Way's journey through space is part of this broader motion. It orbits within the local group, while the group itself drifts within the supercluster. These layers of movement overlap gently, forming nested paths that extend from stars to galaxies to clusters and beyond. None of these motions are felt directly. From within the Milky Way, the night sky appears stable. Stars maintain their positions. Constellations change only subtly over long periods. The broader motion of the galaxy and its group unfolds far beyond immediate perception. This layered movement reflects the universe's structure. Smaller systems move within larger ones. Local motion exists within broader patterns. Each scale follows the same physical principles, guided by gravity acting across distance. There is no need for coordination. The structure emerges naturally from interaction over time. These groupings help explain how matter remains organized. Without gravity linking galaxies together, expansion would gradually pull everything apart. Instead, gravity provides cohesion where mass is sufficient, allowing groups and clusters to persist even as space stretches between distant regions. The local group represents one quiet neighborhood among many. Throughout the universe, similar groupings exist. Galaxies gather where conditions allow, forming collections that move together through expanding space. Each group reflects its own history of formation and motion, shaped by mass and distance. As you rest with this idea, there is no need to picture exact arrangements or trace individual paths. It is enough to sense layered movement. A galaxy traveling within a group drifting within a larger structure, all of it unfolding slowly, without direction or destination, guided by gravity and time. Our place in the universe is not defined by position or importance. It is defined by participation. The Milky Way participates in the same large-scale motion as countless other galaxies, following the same physical rules embedded within the same expanding space. This quiet belonging does not demand attention or comparison. It simply reflects how matter organizes itself over long spans of time, forming groups, clusters, and superclusters that move together, gently and persistently. As we continue, This layered motion opens the way to another subtle feature of the universe, where energy travels beyond visible light, revealing aspects of space that extend beyond what eyes alone can detect. What we see as visible light is only a small portion of a much broader range of energy. Beyond the narrow band that human eyes respond to, light continues in many other forms, each traveling through space in the same quiet way, carrying information without sound or resistance. This broader range is known as the electromagnetic spectrum. It includes light with longer wavelengths, such as radio waves and infrared, as well as light with shorter wavelengths, such as ultraviolet, X-rays, and gamma rays. All of these forms move at the same constant speed through space. What differs is how they interact with matter and how much energy they carry. Infrared light reveals warmth. It is produced by objects that emit heat, including stars, planets, and clouds of dust. Even regions that appear dark in visible light may glow softly in infrared, revealing structures hidden from ordinary sight. This allows astronomers to observe areas where new stars are forming or where dust obscures visible light. Radio waves travel with very long wavelengths. They pass easily through gas and dust, carrying signals across enormous distances. These waves reveal motion, magnetic activity, and subtle interactions between particles in space. They also allow the study of regions that would otherwise remain unseen. Ultraviolet light carries more energy. It often comes from hot stars and energetic regions. X-rays reveal even more energetic processes, such as matter interacting near dense objects or within active regions of galaxies. Each type of light highlights different aspects of the universe, not by changing what exists, but by showing different layers of the same reality. Magnetic fields also fill space. Though extremely weak compared to those on Earth, they extend across galaxies and clusters. These fields guide the movement of charged particles and influence how energy flows through space. They are invisible on their own, yet their presence shapes motion and structure subtly over time. Radiation moves continuously through the universe. Light travels outward from stars, galaxies, and other sources, crossing vast distances without interruption. It passes through regions of open space, through gas and dust, and through areas filled with magnetic influence. Along the way, it carries information about temperature, composition, and motion. Temperature in space varies gradually. Regions near stars are warmer, while areas far from energy sources remain extremely cold. These differences are not abrupt. They change gently across distance, forming smooth transitions rather than sharp boundaries. Even the coldest regions still contain energy, just spread thinly across space. Because light exists in many forms, observation depends on perspective. Different instruments are designed to detect different wavelengths, each revealing a distinct view of the universe. Together, these views combine to form a more complete understanding, though no single perspective captures everything at once. Much of this light passes unnoticed. It travels through space regardless of whether it is detected. It does not depend on observers or instruments to exist. Light continues its journey, whether it is measured, recorded, or never encountered at all. This unseen movement contributes to the quiet activity of the universe. Energy flows. Fields extend. Particles respond. none of this requires visibility to persist. The universe does not limit itself to what can be seen. It includes layers of interaction that unfold beyond human senses. As you rest with this idea, there is no need to imagine every wavelength or trace each path. It is enough to sense that space carries more than meets the eye. Light exists across a wide range, revealing warmth, motion, and structure in different ways, all moving steadily through the same expanding universe. What we see is only one layer. Beyond it, light continues traveling, carrying information through space without sound or disturbance. These unseen forms of light add depth to the universe, quietly expanding perception without requiring effort or focus. As we approach the final section, this broader view of light and energy prepares the way for a gentle closing, where change continues, activity softens, and the universe settles into its long, steady future. As we come to the end of this journey, the universe continues exactly as it always has. Stars keep shining until their fuel slowly changes. Galaxies drift through space, carried along by gravity and expansion together. Light continues traveling, moving steadily across distances too large to picture all at once. Nothing needs to pause for this moment to pass. Over very long spans of time, visible activity becomes less frequent. Distances grow wider. Energy spreads more thinly. The universe trends toward cooler, quieter conditions, not as a destination, but as a natural continuation of expansion and change. Even as this happens, the underlying rules remain the same. Gravity continues to shape matter wherever it exists. Light continues moving long after it is emitted. Space continues stretching evenly in every direction. These processes do not depend on observation. They do not require recognition. They simply persist. Much of the universe remains beyond direct perception. Some regions are too distant for their light to reach us. Others do not emit light at all, yet they remain present, participating in the same slow unfolding as everything else. The universe does not reveal itself all at once. It allows understanding to arrive gradually, carried by light and time together. Nothing in the universe rushes toward an ending. Change unfolds quietly. Structures last for immense spans. Motion continues without sound. Cooling happens gently. What exists now becomes part of what comes next, without sharp transitions. As you rest here, there is nothing left to follow. The universe does not require effort to comprehend. It does not ask to be held in focus. These ideas can remain in the background, the way distant stars remain in the sky, whether they are noticed or not. Space continues expanding. Matter continues circulating. Light continues its long journeys. And within all of that, rest is easy to find. Thank you for spending this time here, moving slowly through the universe together. Wherever you are listening from tonight, may the quiet continue to settle in, carried gently forward, just like everything else. Good night.